Hey everyone, and welcome. Today we are diving into some really cool research to unlock 3 secrets about how our brains and other super smart systems actually do what they do. You're going to want to hear this.
So let me ask you this. What could a secret map, a totally messy toy box, and a teeny tiny computer possibly have in common? I know, it sounds like the start of a weird joke, right? But the answer actually reveals 3 fundamental rules for how we see the world, how we remember things, and even how we're starting to build totally new kinds of intelligence.
All right, let's get into our first secret, the brain's secret map. This tackles a massive puzzle. I mean, think about it. There are billions of us, each with our own unique brain. So how on earth do we all manage to see the world in basically the same way? This is absolutely essential for us to communicate and work together. Well, it turns out the answer is that our brains all seem to use this shared secret map. Now, this isn't a map of roads and cities. It's a map of concepts. It's the reason why, when I say the word house, the idea that pops into your head is fundamentally the same as the one in mine. It's what keeps our understanding of the world consistent.
So, how does this map actually work? You might think that for us to see the same thing, we'd all need the exact same neurons firing in the exact same way. That's the idea on the left, activation pattern coding. But what this new research suggests is something way more clever. It's all about what you see on the right, relational coding.
And here is the key idea. Your brain doesn't really care about the exact neural pattern for face. What it cares about is the relationship, the distance, you could say, between the face pattern and the house pattern and the tool pattern. It's the geometry of our thoughts that stays the same for all of us. This is a perfect way to visualize it. Think about it like this. My internal map of concepts might be kind of rotated compared to yours. But as long as the distance from New York to Los Angeles is the same on both of our maps and the angles are all preserved, we can both navigate the world just fine. The structure is the same, even if the specific patterns are a little different. And look, this isn't just some neat theory. The researchers actually found that this model led to a striking and significant enhancement in consistency between people. They're basically saying that these relational geometries are an essential code for how we share a visual world. It's the stable blueprint for how we see.
Okay, so if the brain has this amazing, stable map, that brings up another question. How does it keep that map from getting all cluttered and messy? Well, the answer is our second secret, and it's a bit of a shocker. It turns out forgetting isn't a bug. It's actually one of the brain's most important features.
Just imagine a toy box where you never, ever get rid of anything. Pretty soon it would be overflowing. You wouldn't be able to find your favorite toy. You couldn't even shut the lid. And the sources say our brain is just like that. If we remembered every single thing, we'd be completely overwhelmed. Forgetting is actually what keeps us sharp and focused. So who's the super helper cleaning out this mental toy box? It's a chemical you've definitely heard of, dopamine. Yeah, we always think of it with learning and rewards, right? But this new research shows it has another huge job. It's a cleaner that actively helps us forget stuff. This isn't just memory fading away. It's a deliberate, finely tuned process. And how do we know this? Well, thanks to some tiny little worms. Scientists looked at C. elegans, which, believe it or not, share a lot of molecular stuff with us. And what they found was that worms that couldn't make dopamine held on to memories for way longer. They just couldn't clear out old information, which strongly suggests this is a fundamental brain function for all of us.
So, you see, forgetting is not a failure. It's the brain's dynamic management system hard at work. It's constantly tidying up, making sure that the really important things, all those core relationships on our secret map, stay clear, accessible, and ready to use.
Okay, so we've got a stable structure for how we see and a dynamic system for how we remember, which brings us to our third secret. What if we could actually build something that works the same way? Well, researchers are now creating tiny computers from molecules that literally fight in order to think.
This thing is called a recursive enzymatic network, or ERN for short. The easiest way to think about it is like a microscopic Lego set. You've got 7 enzymes, think of them as little workers, and 7 peptides, which are like the puzzle pieces. And the real magic starts when you put them all in a room together and let them interact. So here's the play-by-play. The network gets an input, like a change in temperature. That simple change kicks off a fierce competition. All the little puzzle pieces start fighting over the available worker enzymes. This biochemical chaos creates a really complex chemical output, which can then be read as a clear decision. And you might be wondering, what can this tiny computer actually do? Well, the results are pretty stunning. It can act like a simple thermometer, sure, but it can also make switch-like yes or no decisions. And maybe the coolest part is something called tuning. It creates a pulse-like response that the researchers point out is incredibly similar to what we see happening with neurons in our own brains.
So, let's step back and put all three pieces together. We've got the secret map for seeing, the dopamine-powered cleaner for remembering, and this tiny computer that mimics these biological tricks. These aren't three different stories. They are three deeply connected pillars of what makes a system, any system, intelligent. This table really pulls it all into focus. That relational coding, our secret map, that gives us structural stability. Dopamine and the process of forgetting, that's the dynamic management that keeps the structure useful. And these new enzymatic networks, that's neuromorphic emulation. Us trying to build systems that copy this beautiful dance between structure and dynamics. So here's the real punchline. You can't have one without the other. That stable map is totally useless if it's buried in clutter. And a cleaning system is pointless if there's no structure to maintain in the first place. Understanding how these two work together is the real key. And now we're learning how to build it ourselves, right from the molecules up. And all of this leaves us with one last, huge question to chew on. We've just figured out three powerful rules that biology uses to think. As we get better and better at building artificial brains and molecular computers, what other secret rules, hiding in plain sight all around us in nature, are we going to need to learn next? Something to think about. Thanks so much for diving in with me on this one.
Welcome back to the deep dive. Today we're jumping into something really fascinating, kind of bridging these different worlds.
Yeah, it's a really interesting mix. We've got visual neuroscience, the sort of nitty-gritty of neurochemistry, and even synthetic biology.
Exactly. And our mission really is to try and uncover this kind of blueprint for how biological systems manage information processing. You know, how does messy dynamic life produce something reliable?
It's a fundamental question, isn't it? How does the nervous system stay coherent? All these sources we're looking at, they're grappling with this core paradox.
Which is?
Well, how do you balance a really robust, sort of unchanging structure, the blueprint as you called it, with all the constant active management and, frankly, chaos happening inside? How can you have a stable representational geometry, this fixed map, inside a system that's always changing, learning, and even actively forgetting things?
Right. That's the key tension. And the exciting part of this deep dive is putting these pieces together. Because the main takeaway, the kind of core idea from all this material, seems to be that relational geometries are an essential cortical code underlying shared human visual perception.
That's the stable structure right there.
Yeah. And we're going to unpack what that actually means. Geometrically, we'll explore why this active forgetting thing is actually crucial for the system that uses this code.
And then look at how scientists are trying to, well, build systems that mimic this whole complicated dance.
Exactly. Synthetic chemical networks trying to do what the brain does.
It really defines the conditions for biological success, doesn't it? You need the structure, the dynamics, and then this kind of competitive way of implementing it all so they can coexist. But the structure, that invariant code, that probably has to come first.
Okay, so let's start with that structure, the stable part. The visual cortex seems like the place to begin. We're looking at some foundational research here from Littman, Grossman, and others.
Right, and they tackled a really basic fundamental question. How is it that you, me, and you, the listener, can all look at the same thing and, well, basically see the same thing? How do we perceive the visual world in a shared way?
Which is essential. I mean, for communication, right? If my idea of red is totally different from yours, or if how face relates to house in my brain is completely unlike yours, well, talking about them becomes impossible.
Absolutely. And it's not just about our brains being physically similar. The core idea here, and it's crucial, is this. If we find a neural code that's reliably preserved across lots of different people.
Despite all our differences. Brain size, wiring experiences.
Yeah, despite all that variability. If a code holds up, it's very likely playing an essential functional role. It's not just noise or some personal quirk. We're hunting for the universal language of vision.
Okay, so finding this universal language, that sounds hard. How did they actually do it? They looked at the high-order visual cortex, right? The parts that handle complex stuff like faces and tools.
They did. And they needed really high-resolution data. They managed this by working within specific clinical situations, using something called intracranial EEG, or IEEG.
Ah, so recordings from electrodes placed directly on the brain surface.
Exactly. It was part of pre-surgical monitoring for 19 epilepsy patients. It's invasive, obviously, but it gives you incredible detail, spatially and temporally, that you just can't get otherwise. They analyze data from 244 different recording contacts in these high-order visual areas.
Okay, and what exactly were they measuring at those contacts? What signals?
They were looking at changes in high-frequency broadband power, or HFA. And think of it like this. When a group of neurons gets really active, maybe responding to a picture, they use a lot of energy.
Right.
The HFA signal captures that aggregate activity. It reflects the overall local firing rate of the neuron population. It's a good proxy for how active that little patch of cortex is.
Got it. So before diving into complex models, did they check the simple idea, like, is the same physical spot in my brain doing the same job as that spot in your brain? If contact #10 is in my face area, is it in yours too?
They definitely checked that, and they found that just looking at anatomical consistency, the same coordinates, was only weakly correlated with what the neurons were actually tuned to.
Only weakly. So location isn't everything.
Not even close.
Yeah.
There was a lot of local scatter, meaning nearby locations could be doing quite different things across individuals.
Yeah.
It really highlights the challenge.
Yeah.
You can't just rely on the brain's physical address book. You need to find the consistent functional relationship between concepts, regardless of where exactly they live.
Okay, so let's get into that functional relationship. They tested 3 different ideas, 3 coding schemes for how visual information might be consistently represented across these different people. What was the first one?
The simplest model was activation pattern coding. Think of it as a directional model. It basically assumes that the specific pattern of brain activity for, say, seeing a dog should point in roughly the same direction in neural space for everyone.
Like a vector. The dog vector should be parallel in all our brains.
Essentially, yes. Similarities measured by cosine distance are the vectors aligned. It's the most basic idea of invariance.
But probably too simple for messy biology.
Well, it's quite strict. If my whole internal map for vision is just slightly rotated compared to yours, this model breaks down, even if all the internal relationships are perfect.
Okay, so model number 2 went to the other extreme, maximum flexibility.
Exactly. That was linear coding. This model assumes the pattern is preserved, but it allows for any general linear transformation.
What does that mean in practice?
Think of it like taking the neural pattern for dog and allowing it to be arbitrarily stretched, shrunk, rotated, flipped, even sheared, like distorting a picture in Photoshop across different people. This model has the most mathematical freedom, the most degrees of freedom.
So in theory, it should be the best at fitting the data, right? Because it can bend and warp however it needs to.
You'd think so. If the brain just stored concepts, but allowed massive individual warping of the conceptual space, linear coding should capture that perfectly. It's designed to find any linear relationship.
Okay, spoiler alert, I guess it didn't win, which brings us to the third model, relational coding.
Right. This is the winner. And it's based on a more structuralist idea. It proposes that the crucial information isn't the activation pattern itself or even some arbitrarily warped version of it. Instead, it's the set of similarities and dissimilarities, the geometric distances between the patterns for different things.
Okay, wait. So it doesn't matter exactly where my brain represents face, but what matters is how far that face representation is from my tool representation and from my house representation. And that pattern of distances must be the same for everyone.
Precisely. The specific coordinates are subjective, but the geometry of the relationships between concepts is objective and shared.
That's a really neat idea.
It is. And this is where the geometry gets really interesting. For relational coding to work, it mathematically requires that the activation patterns across individuals are similar up to an orthogonal transformation.
Okay, orthogonal transformation. That sounds technical. Can we break that down?
Let's try an analogy. An orthogonal transformation is basically an angle-preserving transformation. The most common examples are rotation and reflection, like flipping something in a mirror.
Rotation, like spinning something.
Exactly. Imagine a simple cube. If you rotate it in space, the absolute coordinates of its corners change, right? They move.
Sure.
But the important stuff stays the same. The angles between the faces are still 90 degrees. The relative distance between any two corners doesn't change. The cube structure is preserved.
Ah, I see. So applying that to the brain, if I see a face and a tool, and in my brain's high-dimensional map, those concepts are separated by, let's say, a certain angle of dissimilarity.
Yeah, like 75 degrees, conceptually speaking.
Then for you, the listener, your face and tool concepts might be in a totally different spot on your internal map, like the whole map is rotated compared to mine.
Right.
But the angle between face and tool must still be that same 75 degrees. The relative distances, the relationships, are locked in.
That's the idea. The brain prioritizes preserving the map's scale and angles, the internal geometry, even if the entire map is oriented differently relative to some absolute coordinate system.
Okay, so they tested these three models, activation pattern, linear, and relational. How did they compare? You mentioned testing on independent data was key.
Absolutely critical. They used a measure called the Intersubject Similarity Index, ISSI,
Right.
and crucially, they evaluated the models on a validation dataset data the models hadn't been trained on. This prevents overfitting, where a model just memorizes the training data noise.
Right. And what happened with that super flexible linear coding model, the one that could stretch and shear? Did its flexibility help on the new data?
That's the fascinating part. Linear coding, with all its flexibility, actually did the best during the initial training phase. It was great at describing the data it saw first.
As you'd expect, maybe.
Yeah, but when they tested it on the separate independent validation set, its performance tanked. It often did worse than the simpler relational coding model.
Wait, why? If it's more flexible, shouldn't it capture everything the relational model captures plus more? How could flexibility be a bad thing?
Because the brain's invariance isn't arbitrary, it's constrained. Linear coding overfitted. It started modeling relationships that were just noise or weird quirks specific to the individuals in the training set.
Ah, so it was modeling arbitrary stretching and shearing that the real brain simply doesn't do when representing concepts across people.
Exactly. The brain doesn't just randomly squish or stretch its conceptual map between individuals. The evidence suggests it primarily rotates it. Linear coding's extra flexibility allowed it to fit those non-existent distortions in the training data, which hurt its ability to generalize to new data. It lost the universal signal in the individual noise.
But relational coding, the angle-preserving one, did find that universal signal.
It did. It showed a robust and consistent increase in similarity, ISSI, compared to the basic activation pattern model. And crucially, this improvement held up strongly on the independent test set.
So it wasn't just a fluke of the math.
No, it strongly suggests that preserving these relational distances is a genuine cortical feature. It's the core structural language the brain uses for shared vision.
Okay, so the bottom line from this first big piece is the brain cares more about the relationships between concepts, the angles, the distances in this high-dimensional neural space than about the specific location or pattern of activation for any single concept.
That's it. This relational geometry is the stable structural blueprint that allows us all to basically agree on what we're seeing, even though our individual brains have their own unique orientations.
That's a really powerful idea, the stable geometric blueprint. But like you said earlier, the brain isn't some static crystal. Well, it's biological, it's dynamic. Neurons change, connections get pruned, new information is always flooding in. How can a stable code like that possibly survive in such a constantly churning environment?
That's the perfect transition to the second pillar, dynamics.
Right.
That stability you just described doesn't happen passively. It requires active management. And this leads us to something really counterintuitive, forgetting.
Right. We usually think of forgetting as, a mistake, a failure of memory.
We do. But the research we're looking at here flips that script completely.
Yeah.
It identifies forgetting not as a failure, but as an essential, actively controlled process. It's necessary for the whole system to work computationally.
So forgetting isn't a bug, it's a feature. Like designed in obsolescence for memories.
Kind of, yeah. Think about the alternative. Imagine if you remembered absolutely everything. Every single sight, sound, smell, every fleeting thought, every trivial detail forever.
That sounds overwhelming.
It would be crippling. The system would quickly suffer from saturation, just running out of space, metaphorically speaking, and retrieval problems. How would you find the important memories buried under mountains of useless trivia? Active forgetting keeps the system clean, flexible, and able to focus on what's relevant now. It preserves the capacity to learn new things.
Okay, that makes sense. But what drives this active forgetting? Is it just decay?
That's the really surprising part. It seems to be actively driven by a specific chemical, dopamine.
Dopamine, but isn't that the reward chemical? The one involved in motivation and learning and strengthening memories?
Exactly. That's what makes it such an elegant regulatory loop. Dopamine is involved in reinforcing a new memory, making it stick initially. But evidence suggests it also kicks off the process for eventually clearing that memory out.
So the same molecule hits the gas and then later the brake.
It seems that way. It's a tightly integrated system where the mechanism for acquiring information also manages its lifespan and disposal. It prevents the system from being permanently cluttered by everything it ever learned.
Is there solid molecular evidence for this? How do we know dopamine is actively doing the forgetting?
There's some compelling evidence, particularly from model organisms, where you can really get precise control. Studies in C. elegans, the little roundworm, are quite revealing here.
Okay, hold on. A worm, it only has, what, 300 neurons? How relevant is worm memory to our 86 billion neurons?
That's a fair question, and always important to keep scale in mind. But the reason we study these simple systems is that many fundamental biochemical pathways are incredibly ancient and conserved across evolution. What works in the worm often points to similar mechanisms in us.
Okay, so what did they find in the dopamine-deficient worms?
They found that worms genetically engineered so they couldn't produce dopamine held on to learned associations for a significantly longer. They essentially couldn't forget properly. It took much more effort, much longer training protocols to get them to extinguish an old memory.
So removing the forgetting chemical made the memory stick around too long, becoming maladaptive.
Precisely. It gummed up their ability to adapt. And they drilled down even further, identifying specific dopamine receptors involved. One called DOP2 seemed to actively promote forgetting. When it was more active, memories decayed faster. Another, DOP3, seemed to modulate or fine-tune this process.
And these worm receptors have counterparts in humans.
Yes, they're structurally related to dopamine receptors found in our brains. This strongly suggests that this idea of active dopamine-driven forgetting isn't just a worm quirk, it's likely a universal brain function, a fundamental strategy for managing computational resources across vastly different scales of complexity.
Okay, so now we can connect it back. The relational coding gives us the stable shared geometry, the blueprint.
That's right, the invariant structure.
But that structure can only persist and remain useful despite this constant, necessary churn managed by dopamine-driven forgetting.
That's the crucial link. The active forgetting, the dynamic management, prevents the system from becoming so saturated and noisy that the stable relational code gets lost or becomes impossible to retrieve efficiently. The brain's strategy isn't to build a perfectly static library, but to build a stable structure that can survive within a dynamically managed, constantly refreshed library.
Okay, so we have the stable blueprint, the relational geometry, and we have the dynamic management system, the dopamine-driven forgetting that keeps the system functional. The next big question is, how? How does biology actually implement this balancing act?
Right, what's the mechanism? And for that, we turn to our third area, synthetic biology. Researchers are trying to build artificial systems that can mimic this kind of biological computation, but using chemistry instead of silicon. They're creating things called recursive enzymatic networks, or ERNs.
Okay, neuromorphic systems in chemico. That sounds ambitious. What's the basic idea?
The idea is to take inspiration from how complex networks operate inside cells, and also borrow ideas from a computational approach called reservoir computing. They want to see if they can get complex, brain-like computation to emerge from interacting chemicals.
So what are the building blocks? What's actually in the network?
In the specific example we looked at, they used 7 different enzymes, mostly proteases, which break down proteins, and one called alkaline phosphatase, which modifies molecules. These enzymes were immobilized, stuck in place.
Okay.
And then they had 7 different peptides, short protein fragments flowing through the system. The key is the environment. It all happens in a continuous stirred tank reactor, a CSTR.
CSTR, continuous flow, constantly mixing.
Exactly. Input chemicals flow in, react, and products flow out. It mimics the open, non-equilibrium nature of biological systems, always interacting with their environment. It's not a closed box.
So you've got these enzymes and peptides constantly mixing and reacting in this flow-through reactor. How does that lead to computation? What does the processing happen?
The computation emerges from the recursive competition for resources. The enzymes compete to act on the peptides. Proteases break them down. Phosphatase modifies them. This creates really complex feedback loops and nonlinear interactions.
Nonlinear meaning the output isn't just proportional to the input.
Right. Small changes in input, maybe temperature, or the concentration of a specific peptide can cause big, complex changes in the internal state of the chemical network as all these reactions adjust and compete. That complex internal state is the computation.
Okay, this is where that reservoir computing idea comes in, isn't it? Can you unpack that a bit?
Yeah, so in reservoir computing, you have this complex dynamic system, the reservoir. In this case, it's the churning network of enzymes and peptides in the CSTR.
Okay.
The key idea is that this reservoir naturally takes any simple input signal and projects it or maps it into a much richer, higher dimensional, complex internal state. The beauty is you don't need to precisely program the complex dynamics inside the reservoir. It just sort of happens because of the interactions.
So the complexity is emergent.
Exactly. All you need then is a relatively simple readout layer, often just a linear machine learning algorithm that learns to interpret the complex state of the reservoir and map it to the desired output.
So the complex chemistry does the hard, nonlinear work internally, and the simple algorithm just learns to read the chemical fingerprint that
You
results.
got it. The nonlinearity, the computational power, comes from the chemical competition and feedback, much like how intricate patterns of excitation and inhibition between neurons create computational power in the brain.
Okay, cool concept. But does it actually do anything useful? Can it perform tasks that we'd recognize as, well, brain-like?
Surprisingly, yes, it demonstrated some pretty general capabilities. For example, sensing. They tasked the ERN with estimating the absolute temperature inside the reactor over a pretty wide range, 25 to 55 degrees Celsius.
Wouldn't temperature just make everything go faster? Seems kind of linear.
You'd think, but because you have 7 different enzymes and 7 peptides all competing, their reaction rates change differently with temperature, making the overall system response highly nonlinear and complex. And it was remarkably accurate. The average error was only about 1.3 degrees Celsius across that 30-degree range. It acted like a complex, self-organizing chemical thermometer.
Wow, okay. What about more abstract stuff, like logic?
It could handle nonlinear classification tasks too. These are problems that simple linear models can't solve, like the classic XOR problem, or classifying points inside a circle versus outside, or in an hourglass shape. The ERN could learn to classify inputs based on these complex nonlinear boundaries.
That definitely requires transforming the input in a complex way, like we think the brain does.
Right, and maybe the most striking connection back to neuroscience was in its tuning properties. When they looked at how the ERN responded to changes over time, they found it could produce these localized pulse-like responses.
Pulse?
Yeah, a sharp increase in activity followed by a decay, a sort of gradient response. The researchers noted this was qualitatively similar to the firing patterns of neurons in the brain.
Whoa. So a chemical soup is mimicking the spiking behavior of neurons.
In a way, yes. It suggests that these dynamics, competition, feedback, nonlinearity, might be fundamental to generating that kind of information processing pattern, whether it's in neurons or in enzymes.
So the ERN research gives us a potential mechanism, a way to understand how biology might generate the complex dynamics needed.
Exactly. It offers a potential chemical paradigm for how you get the nonlinear, competition-based processing that seems necessary to support both the structural stability of something like relational coding and the dynamic regulation provided by things like dopamine-driven forgetting. The stable code needs a complex dynamic engine to run on, and ERNs show one way chemistry might build that engine.
Wow. Let's try and pull all these threads together for everyone listening. We've gone from this incredibly precise geometric code in the visual cortex
The stable blueprint.
through the seemingly destructive but necessary process of chemical forgetting driven by dopamine in worms,
The dynamic management.
all the way to these synthetic competing enzyme networks in a vat that seem to mimic brain-like activity.
The implementation mechanism.
How do these three structure, dynamics, emulation form one coherent picture? What's the grand synthesis here?
Yeah, this is the so what moment,
Okay.
right? What these 3 pieces give us together are the essential ingredients for successful advanced biological computation. They define the necessary conditions.
Okay, lay them out for us.
Pillar 1, relational coding. This provides the structural stability. It's the invariant blueprint, the shared geometric map in the high-order visual cortex that ensures we perceive the relationships between concepts consistently. It's the foundation of shared meaning.
But a static foundation isn't enough in a dynamic world.
Precisely. That leads to pillar 2, dopamine-driven forgetting. This is the dynamic management. It's the active, chemically controlled process of clearing out old or irrelevant information to maintain computational capacity, flexibility, and efficiency. It ensures the stable structure doesn't get buried or become rigid. It keeps the system adaptable.
So structure provides the meaning, dynamics provides the maintenance and flexibility. What about the third pillar, the ERNs?
The enzymatic networks provide the neuromorphic emulation, or maybe better, they illustrate the type of implementation mechanism required. They show how complex nonlinear dynamics, driven by competition and feedback, can generate the sophisticated processing needed to support both the stable geometry and the dynamic regulation. They're a model for the engine that runs the whole show.
Okay, so the core conclusion we started with really holds up then, that relational geometries are the essential cortical code for shared vision. That's the stable structure.
Yes.
But it only works, it's only biologically successful because it exists within a system that's actively managed through dynamics like forgetting, driven by specific chemistry.
Right.
And the whole thing, stability and dynamics, is implemented through these complex, competition-based network interactions that systems like ERNs are starting to help us understand.
That's the synthesis.
Yes.
The success hinges on this dynamic tension. You need the stable relational geometry for shared understanding, but you need the dynamic regulation like forgetting so the system doesn't collapse under its own weight. And you need complex competitive network dynamics to make both possible. Remove any piece, and the whole thing likely fails.
It paints a picture where the bedrock of our shared reality isn't a specific thing stored somewhere, but rather this abstract mathematical pattern, this geometry of relationships constantly being maintained amidst chemical chaos and competition. That's quite something.
It's a very different way of thinking about how the brain achieves consistency. #OutTro. Final thoughts and exploration.
Well, we really went on a journey there. We started with what seemed like pretty separate lines of research: visual neuroscience, worm memory, synthetic chemistry.
Yeah, seemingly disparate fields.
And we've ended up with this unified view, all revolving around the power of this stable relational geometry maintained by dynamic processes.
It really does tie together nicely, and it leaves us with some pretty deep questions, especially about our own experience.
Like what?
Well, if these relational geometries define our shared visual perception, if they are the common code, it makes you wonder, does this imply that even if my subjective feeling of seeing the color red, the quail, the raw experience is totally different from your feeling of seeing red?
Which seems possible, even likely.
That the relationship between our concept of red and our concept of blue or red and green or red and chair, the geometric distance and angle between those concepts in our respective neural spaces is actually fundamentally the same for both of us.
Whoa. So the internal color on my mental map might be unique to me, but the structure of the map itself, the distances and angles between all the locations, is universal.
That's the provocative thought, isn't it? What are the implications if that's true? For understanding consciousness, for psychology, dealing with subjective reports, even for building artificial intelligence. If we could capture that invariant relational structure, maybe that's the key to a robust, human-like understanding that doesn't overfit like that simple linear coding model did.
A shared structural reality beneath the surface of subjective experience. That is definitely something to mull over.
A deep structural commonality.
Thank you so much for walking us through all of that. It really connected the dots in a fascinating way.
My pleasure. It's always exciting to see how structure emerges from dynamics.
Absolutely. Keep exploring these deep connections. We'll see you next time on The Deep Dive.
Have you ever watched a chess grandmaster play and just thought, how on earth did they see that? It's an amazing question, really. And the answer connects the deepest secrets of how your own brain works to the brilliant, high-stakes strategy of chess. So let's dive right in. How do their brains see moves that feel completely invisible to the rest of us? Well, it turns out there are two incredible secrets behind their genius. A secret map that, believe it or not, you share with them, and a tiny but incredibly powerful computer built from molecules. All right, first up, let's talk about that secret map. We're going to look at how a grandmaster's brain can instantly see the hidden structure of the board and use it to zero in on a critical weak spot that's there in every single game. It all kicks off with this core brain principle called relational coding. And this is not just a chess thing, not at all. This is the fundamental reason all of our brains can see the world in a consistent way. It's how we make sense of everything. The easiest way to think about it is to imagine your brain has this secret map. It uses it for everything, whether it's recognizing a friend's face or figuring out a chessboard. And here's the wild part. We all share the same basic blueprint for this map. And this slide really hits the nail on the head. Your brain's map couldn't care less about the exact coordinates of things on the board. What it cares about are the relationships, the patterns, the angles, the distances between the pieces. It's why you recognize a friend, whether they're up close or across the street. The relationship between their eyes, nose, and mouth stays the same. Okay, so how does this map help in a chess game? It lets a player instantly spot what is, structurally, the single biggest weakness on the entire board right from the start. Now, the weakness of that f-pawn isn't just some random rule you have to memorize. No, it's a geometric truth. It's all about its relationship to the king. See, at the beginning of the game, it's the only pawn that's defended by just one piece, and that piece happens to be the king, the most important one you've got. This creates a fixed, unchangeable weak point no matter what else is happening. And because of relational coding, a grandmaster's brain doesn't have to sit there and analyze this every time. Their internal map just sees that weak structure, that specific geometric relationship, and it recognizes it automatically. It's as effortless as you recognizing your own house. It just knows. Okay, so their brain's map has spotted the weak point. That's a huge advantage. But, seeing it is one thing. Deciding what to do about it, that's a whole other ballgame. And that brings us to our second secret, the brain's tiny little computer. Now, this idea is modeled by something with a very fancy name, a recursive enzymatic network. Don't worry about the term. Just picture this, a biological computer. It's a super powerful processor, but instead of silicon chips, it's built from tiny molecular puzzle pieces floating around inside our cells. So how does this thing even work? Well, it runs on competition. You can imagine all these little molecular pieces are constantly fighting each other for resources. And this constant battle creates this incredibly complex, incredibly fast system that's just perfect for making the kind of tricky, multi-step calculations you need in a game like chess. So, we've got this tiny biological computer. How does that actually help a player turn what their secret map is telling them into a real, concrete, winning plan on the board? Well, its power is that it's an amazing multitasker. It's constantly classifying the position. Is this safe or is this dangerous? It handles those big switch-like decisions. Do I attack or do I defend? And maybe most impressively, it can calculate those really complex tactics where the best move isn't obvious at all. It goes way beyond simple logic. And this is absolutely essential for those moments of pure genius you see in a chess match. Like a tactical sacrifice, giving up your queen, your most powerful piece, to guarantee a checkmate a few moves down the line. If you're just counting points, that's a terrible move, but this tiny computer can process that deeper, nonlinear path. It sees the victory that others miss. This kind of processing power is also the key to something we could call impression management. It's not just about playing the pieces, it's about playing the player. A grandmaster can use it to set up a deep, hidden trap by making it look like they're ignoring a weakness, all while their brain is calculating the perfect moment to spring that trap. So now, let's bring these two incredible secrets together, because they don't work alone. Let's see how they create a single, masterful mind. So here's the bottom line. A grandmaster needs both of these tools working in perfect harmony. They need that stable secret map to instantly see the unshakable truth of the position. Hey, that F-pawn is weak, and then they need that flexible tiny computer to make the complex, creative, and often shocking decisions to actually exploit that truth and win the game. And that leaves us with a pretty fascinating final thought. Chess is like this amazing window into our brain's operating system. But these same tools, this structural map and this tiny, powerful computer, they're humming away inside your brain right now. So the real question isn't just about chess, is it? It's what else are they truly capable of?
Welcome to the debate. Today, we are diving into one of the most, compelling questions in computational neuroscience. How does the brain actually achieve strategic excellence? And this isn't just theory, right? This debate springs from emerging data suggesting that specific molecular and perceptual mechanisms are really core to neuroplasticity and function.
Exactly. And we're using chess, which is arguably the ultimate laboratory for complex decision-making, to explore how two key computational mechanisms, relational coding, or RC, and recursive enzymatic networks, ERNs, underpin high-level strategic thought.
Right, so the central question we face is this. In the context of strategic expertise, like in chess, which mechanism plays the dominant role in differentiating, say, a master from an expert? Is it the brain's foundational, stable map for instantly recognizing invariant structure, that's relational coding?
Or is it the brain's specialized capacity for complex, adaptive, nonlinear computation required for multi-step execution, the function we attribute to recursive enzymatic networks?
And I'll be arguing that the recognition of structural truth via relational coding is the essential, foundational driver. Basically, it establishes the reality of the game.
And I come at it from a slightly different angle. While that recognition is certainly necessary, I argue that the ability to execute complex, nonlinear decisions and manage the competitive dynamics of the game, facilitated by these recursive enzymatic networks, is what truly defines and differentiates elite strategic potential.
Okay, so my argument rests on the supremacy of foundational consistency. Superior strategic play, especially in a system as defined as chess, it stems directly from the immediate and consistent recognition of structural truth. And that consistency is the primary function of relational coding. RC is essentially the brain's structural blueprint, you could say, or its foundational grid. It's the code that ensures we care about the fundamental relationships between objects, their relative angle, their distance, not their exact shifting coordinates in space. Think of a simple geometric example. Whether you draw a triangle large or small, rotated or flipped, the relationship between its three angles remains invariant. That stability, that preserved relationship, that's RC at work. Applied to the chessboard, this means that structural weaknesses, like the infamous f2, f7 pawn, that king-pawn relationship, where the pawn is only defended by the king, are instantly recognized across all board variations. RC provides the stable reference frame for the entire game, allowing the player to instantly categorize a position as safe or dangerous based on, well, structural certainty. Learning successful patterns like the scholar's mate setup works precisely because RC makes recognizing that invariant structural relationship easy and consistent. It minimizes the cognitive load, allowing rapid triage of the board.
I appreciate your emphasis on the efficiency and, yeah, the necessity of a stable perceptual anchor, but that stability risks reducing mastery to mere pattern matching. Structural recognition is critical, yes, I grant you that, but it is merely the first necessary step. True strategic mastery is about adaptive execution, which demands highly complex, nonlinear computation, a capacity best modeled by recursive enzymatic networks. The ERN is a remarkable concept, functionally a tiny, super powerful computer built from molecular components. Its defining characteristic is recursive competition among these components, generating a complicated, highly nonlinear network dynamic. This complexity isn't just academic, it's the source of adaptability. It allows the ERN to perform generalized computational tasks quickly, moving beyond simple classification. For the Grandmaster, this means the ERN handles the necessary switch-like response decision-making. Should I attack now or should I defend? It is critical for evaluating whether exploiting that F7 weakness, which RC identified, will actually yield a win in a specific multi-step sequence. Exploitation demands calculating a pathway that far surpasses simple structural classification, requiring the dynamic complexity that the ERN is designed to mimic.
Okay, let's jump right into the heart of the disagreement then. This tension between recognition and exploitation. You place the differentiating factor squarely on the complexity of execution. But I'm not convinced by that line of reasoning, because the effectiveness of that execution is entirely conditional. If the player cannot instantly recognize that invariant king-pawn relationship at f7 using the consistent, stable map provided by RC, the possibility of exploitation never even arises, right? RC provides the foundational certainty. Without that anchor, the subsequent tactical calculations, no matter how nonlinear or complex the ERN makes them, are essentially undirected computational noise. RC doesn't just classify the position, it directs the cognitive resources to the weakness. How can we possibly argue that execution is primary when the execution is entirely dictated by the consistency of the initial perception?
Well, I see why you insist on the primacy of the stable map. But you seem to be framing RC as the entirety of the strategic process, when it's just the initial input filter. RC tells you where the vulnerability is. The ERN tells you how to break it. Let's consider that high-level tactical challenge again, the tactical sacrifice. Imagine a player relying purely on the stable RC map sees the F7 weakness. Okay, an intermediate player might calculate a simple 3-move linear sequence. A master, leveraging the complex dynamics of the ERN, might calculate a 5-move forced sequence that involves giving up a major piece, a queen or a rook, on move 2 to achieve checkmate on move 5. That is a highly nonlinear decision, where simple linear evaluation, like just counting pieces, which the stable RC map supports, fails completely. The ERN's complex architecture mirrors the brain's necessity to calculate these non-obvious, multi-step scenarios. The genius is not in knowing the pawn is weak. Everyone above a certain level knows that. The genius is in executing the non-linear maneuver that proves the weakness is terminal, and that complexity is the hallmark of the ERN.
But wait, doesn't that imply we're talking about two separate biological systems rather than two facets of the same mechanism? The ERN calculation is successful because RC previously established a precise geometrical relationship to finding the target. The calculation is only complex if the initial mapping succeeds. I mean, if the master misinterprets a structural truth due to faulty RC, perhaps overlooking a hidden defender, then that queen sacrifice becomes a fatal blunder, not genius. The structural truth, the invariant map provided by RC, is the objective reality against which the ERN's highly nonlinear prediction must be tested, isn't it?
That's a compelling argument, I'll give you that. But have you considered the element of simultaneous processing, which is vital for competitive strategy, especially what we might call impression management? The game of chess is competitive flow management, right? The ERN's inherent capacity for complex, simultaneous computation, multitask processing, is fundamental here. A master doesn't just calculate one line. They are processing opponent intentions, multiple potential threats, deep tactical setups, all at once. Consider a player who manages the impression of the board by seemingly ignoring that F7 weakness. Instead, they play a slow, prophylactic move that seems passive, maybe controlling a future square of retreat for their king, while their opponent is focused on the immediate threat to F7. This feint, this simultaneous control of different information streams, requires the flexible dynamics of the competing ERN elements to generate diverse, adaptive responses. The success of this move is defined by its strategic depth and its ability to manage the flow of information, which is a generalized computational task far beyond simple pattern recognition.
That's an interesting point, though I would frame it differently. While ERNs clearly handle the, let's say, executive complexity of feints and multitasking, the success of impression management fundamentally relies on the opponent's failure to properly utilize RC, doesn't it? The manipulation only works if the opponent mistakes the superficial linear evaluation for the deeper structural truth being manipulated. If the feint is successful, it's because the opponent has momentarily failed to use their stable map to recognize the preserved geometric relationship, the underlying threat being prepared under the surface. The opponent focuses on the surface impression created by the ERN-driven feint, but if they had perfect RC application, they would instantly see the enduring structural vulnerability being exploited. So the manipulation only works because of the stable map defined by relational coding. It establishes the fixed point against which all temporary manipulation is measured.
I'm sorry, but I just don't buy that the stable map alone explains elite performance, especially when we discuss computational limits. You emphasize RC's efficiency and consistency, suggesting it establishes a foundational blueprint shared by everyone, making recognition easy. And that's true for intermediate players who rely heavily on memorized patterns. But if strategic excellence is purely about recognizing that shared blueprint, why do grandmasters spend countless hours calculating lines far beyond established theory?
The material on NRNs shows that complex systems rely on recursive competition to generate diverse, adaptive responses. Strategic novelty. True strategic genius is about moving beyond pattern recognition, RC, the shared code, to solving generalized computational problems that adapt to unprecedented board states. The NRN is designed precisely to mimic the complex dynamics required for that kind of highly nonlinear adaptive decision-making.
The ultimate ceiling of strategic potential lies in the capacity for this flexible complexity, not in the foundational stability.
But if ERNs are so powerful, why do grandmasters still rely so heavily on that inherited wisdom, on memorizing those structural patterns developed over centuries, which are essentially pure RC? The brain needs to anchor perception. The computational efficiency of RC cannot be dismissed. It allows the master to immediately triage the board, establishing the anchors of vulnerability and defense without taxing the limited resources of working memory. I mean, if every decision required the full recursive computation of the ERN to calculate complex, nonlinear sequences from scratch, the reaction time would suffer immensely.
The genius is that the RC map provides the immediate, efficient categorization, safe, dangerous, allowing the ERN to focus its immense computational power only on the handful of critical decision points directed by the map. The ERN's complexity is directed by the RC map. It doesn't operate in a vacuum.
The memorization of patterns is a scaffolding built for the RC mechanism. I grant you that. But the defining moments of strategic genius are when that scaffolding is voluntarily discarded. We know ERNs handle complex, nonlinear dynamics. They overcome resource limits by finding the non-obvious solution. Look, the moments that define strategic potential are when the simple map fails, when you must calculate a forced checkmate through a tactical sacrifice where the material count is deeply unfavorable according to simple metrics. That necessary calculation, which moves beyond the structural blueprint to multi-step computational depth, must be the differentiating factor. It is the capacity for generalized, adaptive response that defines the elite player.
So, to conclude my side, the ability to achieve consistent, high-level strategy, to instantly recognize structural vulnerabilities like the F2, F7 pawn, and build successful patterns across varied board positions is predicated on the invariant foundational grid of relational coding. RC establishes the stable perceptual reality of the game, providing the efficient anchor needed for all subsequent cognitive processing. It is, I believe, the consistent core code that frames expertise.
And from my perspective, while relational coding efficiently identifies the structural truth and provides that stable foundation, the ultimate strategic victory, the realization of elite potential, requires the flexible, complex processing mechanisms emulated by recursive enzymatic networks. These dynamics are necessary to execute the nonlinear exploitation of those weaknesses, generate strategic novelty, and manage the competitive flow of information in feints.
Right. The material makes a strong case, I think we both agree, that optimal performance likely requires a deeply synergistic relationship, demanding both the stable map RC for consistent recognition
and the flexible processing, ERNs, for complex, tactical execution, yeah. So, we leave the listener to reflect on the question of which mechanism ultimately dictates the ceiling, defining the limits of strategic potential in the grandest games.
Ever wonder how a mastermind's brain really works? Turns out it's not one secret, but two. So, what's the deal with master-level thinking, say in a game as complex as chess? Well, it isn't a single stroke of genius. It's actually two secrets working in perfect harmony. Okay, so secret number one is something we can call the stable map. The technical term is relational coding. Think of it as a shared blueprint for reality. This map helps us instantly see patterns and find those core truths that just don't change. For example, in chess, a master's brain just knows the F2 pawn is always a weak spot. But hey, a map is pretty useless without a navigator, right? That's secret number two. And this is where the recursive enzymatic network, or ERN, comes into play. The ERN is the powerhouse that handles all the messy, real-time, complex decisions. So you've got the map and the navigator. One recognizes what is true, the other figures out how to act. So how did these two pieces actually come together to create that mastermind thinking? It's a really powerful two-step process. First, you identify a truth, then you exploit it. Think of it this way. The map shows you exactly where the destination is. And the navigator? It gets busy plotting the best, most clever course to get there. You see, real success isn't about having just one. You absolutely need both working together. And this idea goes way beyond just a game. It's really a model for understanding reality itself. So the big takeaway is you need that stable map for recognition and a flexible navigator for decisions. It makes you wonder, right? What map and navigator are you using to understand your own reality?